Yeah. So variance. A very important tool. So after this, the arithmetic mean, the arithmetic mean of squares of deviation of squares of deviation squares of deviation taken from arithmetic arithmetic mean is called variance. Look, the definitions itself are going to tell you about the formulas, okay? So, whenever we write down a definition, you should be able to make up the mathematical formula to find the same. I'll also, with the same, I'll also write down it is denoted by, it is denoted by VAR round bracket X or sigma square. Yes, anyone who can tell me what is VAR of X equal to?
Summation of xi minus x bar whole square divided by n minus 1.
Divided by n minus 1 summation xi minus x bar whole square upon
n
n
minus 1.
n. And this will be the formula for which type of data?
raw data.
Raw data. What could be for the discrete and the continuous frequency distribution? Discrete and continuous frequency distribution. Yes, very easy. I mean, it shouldn't be difficult now.
Sir, we just need to add a frequency, I guess,
Where
in the numerator.
nothing else.
Um, then, no, not means along with this xi, along with this xi minus x bar bracket square. I think we need to add frequency also. That is what I feel.
Okay.
And in the on the denominator also.
Denominator it will be
Um, fi.
okay. You're partially right. So the formula will be summation fi xi minus x bar whole square. I is running from 1 to n. Let me just write this n at a proper place. So it will be n over here divided by summation fi. I is running from 1 to n. Okay, so variance plays a very important role. So it is going to give us the deviation, mean square deviation, mean square deviations. Okay, so what is the deviation of all the observations from the mean and its square, and how it is denoted by? It is denoted by sigma square. And why this variance is important? Variance is important because it helps us to find out the standard deviation. So this standard deviation is most commonly used tool to study the dispersion. Okay, and the formula for this is the positive square root of variance is nothing but the standard deviation. So the positive square root of variance is called the standard deviation. Look, we cannot take it as it is. I mean, if the question is asked, define standard deviation, you cannot simply state in the exam that it is a positive square root of variance. No. The way you will have to give the definition is the positive square root of the mean of squares of the deviations. Okay. Mean of the squares of deviations taken from the arithmetic mean. Okay, so you will have to define it in this manner. So what it will be denoted by? It is denoted by
SD.
SD, and it is denoted by
Sigma.
SD and sigma. D and sigma. The formulas for both of them: sigma is equal to under root summation xi minus x bar whole square divided by n. I is running from 1 to n, right? And this is for raw data. Then the other one will be under root summation fi xi minus x bar whole square upon summation fi. I is running from 1 to n. This is for discrete and continuous frequency distribution. This is s dot d of x. This is also the standard deviations. Okay, these are the basic formulas. Okay, but this can be further simplified. How it can be simplified is this. Say I'll write this down as a remark here. So I'll take the first one with the formula for the raw data. Okay, so for the raw data, sigma square, the formula is summation xi minus x bar whole square divided by n, and I is running from 1 to n. So in this, if we square the numerator, what will be the square of this? Xi square minus 2 times xi into x bar plus x bar square total divided by n. Now, so if I open the bracket, so I'll get summation xi square minus, can I take 2 times x bar outside the summation? Is it possible? Is it possible?
Yes, sir.
Because
So we can take that common.
why? Plus,
Because R is running from I to 1 to n.
so what? Can I say that
Bar is a
integrate?
constant.
It is a constant. So is it possible that every time the constant can be taken outside the summation? Is it always possible?
Uh, yes.
Because summation is a kind of integration, right? I mean, integration is for continuous. I mean, whenever you are doing over a interval, okay. Summation is the discrete form of the integration. So whenever a constant is there, constant can always be taken outside the summation. Okay, you can remember that. Now in this case, summation xi square, I'll take separate this denominator xi square divided by n. This is the first term, and this 2 times x bar, as you said, I've taken outside. In the bracket, I will have summation xi divided by n. I is running from 1 to n plus summation x bar square divided by n. I is running from 1 to n. What can you say about the first term? What is it? Now, as we are going into abstract statistics, you should be able to recognize the terms, what you are doing, and you should be able to analyze things. So, what is summation xi square divided by n? Ananya?
So can I say?
Just a minute. Let me see at least she is active or not. Vanshika,
Yes, sir.
what is it? The first bracket, what is it?
So, uh, 2x minus 1.
No, first bracket. Okay, anyway, uh, Suhab,
Yes, sir.
what is this first bracket term? Can you see the operations what you're doing and tell me what it is?
Yes, sir. So variance.
No.
Okay, sir. Yes.
Okay, tell me, Sakshi.
Mean square deviation.
No. It is not a deviation. There is no minus something. Whenever you subtract, that time you get a deviation. It's not a deviation. Can I say that it is the mean of the square of xi?
Yes.
So xi is you're squaring all of them and then you're taking the mean of it. So I will write this down as x square bar.
So will you please repeat it once?
I said that can I say that it is the mean of the squares of xi's?
Okay. Yes.
Can I say that? Drumil, can I say that?
Yes, sir.
Yes. So because you are taking the mean, right? You are squaring all the xi's and then you are taking the mean. Anyway, what is the second term? This is x bar, and what is this term? Bracketed term is again the mean. So it will be x bar square. What is the third term? Who can simplify it now? The third term.
Sir, it may be x cube.
Why? Why is it x cube? Aditya Patil.
So
Yes. Can you simplify the third term? Sakshi?
No, sir.
No. Okay. So x bar square being constant can always come outside the summation, and what we will have is summation I is running from 1 to n. What will remain outside inside is 1. What is this term? Can you tell me? Summation I is running from 1 to n of 1. Saurav? Shivani Swaraj?
Sir, I can't see your screen.
You
Sir,
cannot
the
see.
screen display is gone. Sir,
Okay.
can I answer?
Just a
Yes.
wait. Now?
Yes, now I can see.
Yes.
Huh. Yes, please tell me. Summation I is running from 1 to n round bracket 1.
Sir, can I?
Yes,
Sir, it is nothing but n.
it is nothing but n because you are adding
1
1
n times.
1 you are adding n times.
Yes. And it will cancel out with the n in the denominator, so it will become just x like that.
Yeah.
Sir, again, your presentation is not visible. Again, your screen. It is not visible, sir.
Okay. So this will be x square bar minus 2 times x bar square plus n and n. This will get cancelled out with this. So we have x bar square. So the final formula for variance of x, which is also denoted by sigma square, is equal to x square bar minus x bar square. If I want to write this down in the summation form, the first one will be summation x square I is xi square, I is running from 1 to n divided by n, minus summation xi I is running from 1 to n divided by n bracket complete whole square. I hope it is clear. The same type of calculations I can also do it for continuous or the discrete frequency distribution. For the frequency distribution, variance of x is equal to sigma square is equal to, yes, anyone who can generalize the formula?
Sir, as in the terms of x square sigma x square,
Sigma,
x square, like n into n plus 1 into 2n plus 1 by 6. You're asking that or something else?
no, I want the formula when your data is of the frequency distribution, either discrete or continuous. What can you generalize this formula, the one above one, to the frequency distribution? Ritika, Oza, are you there?
Yes, sir.
Yes, can you generalize this formula for the variance to the frequency distribution form? Ritika, please reply. I am asking you. No? Yes, Polke, you cannot just mute yourself. Tell me. Done. Anyone else? Hasnan?
Sir, I don't know.
Don't know. Others?
I can try.
Yes, Aditya, please.
Summation of fi square xi square upon summation of fi
Okay.
minus in bracket summation of fi xi bracket square upon like summation of fi.
Okay.
So can I try?
You are almost right, Aditya. Yes, Sakshi.
Summation of fi xi whole square divided by fi summation of fi minus summation of fi xi divided by summation of fi whole square.
No. Aditya was almost right. So the meaning is, look, Aditya, the only place where you need to think of is what you're doing is you're making the mean of x square. What will be the mean of x squares? Can you try, Aditya, this one? Summation
Summation xi
xi
square upon
square.
summation of
No, for the frequency distribution. Let's talk about the frequency distribution. In that case, what will be the formula for mean? The formula is summation fi xi upon summation fi. This is when you have the frequency distribution. This is how you get the mean of x.
Sir, can I try now?
No, let Aditya do it because He was almost right. Just one place where he need to change is this. Yes, Aditya, please.
Sir, summation fi square xi square upon summation of fi.
Hmm, okay. Okay. Who was the other one who wanted to try? Please
Me.
go ahead. Yeah.
Sir, summation x minus x bar square by n. Xi minus x bar.
Why you're going to that? I need the generalization of this formula for frequency distribution. Okay. Anyway, so summation. When we say that the mean of x squares I need to find out, I need to multiply the frequency to those variable on summation f. This is how you get the mean. You don't make the square of the frequencies also. It is just the mean of x squares, not x. Okay.
So like we don't have to take the square of
Fi.
fi's. We have to
Yes.
just okay, got it.
Okay. So the formula will be summation fi xi square, I is running from 1 to n upon summation fi, I is running from 1 to n, minus this is going to be summation fi xi, I is running from 1 to n upon summation fi whole square.
So I said the same thing.
Okay, maybe I didn't listen properly then. Okay, but if you said this, then it was right. So look, this formula is quite, I mean, easier than the earlier one. I'll go to the earlier one. So this one. So both the formulas are almost, I mean, this fi xi minus x bar whole square upon summation fi, here there will be I is running from 1 to n, and this and this one. Both the formulas are for variance, these two and these two. But while you are doing the calculations, this formula turns out to be much more what you can say easy, because in first one you will have to find out the mean and then use it to find out the variance in the first formula, this one. So why, if you go by this formula, we will have to find out the mean first, and then we will have to use this formula to find out the variance. Whereas in this, the last formula, you can simply make the columns for fi xi square and fi xi. So using that, we'll directly get the mean. So that's why the second one is much more easier. Fine. So why we are finding this? Okay, so once we have all these formulas, what we are concentrating on is the coefficient of variation, a very important concept here. So all these things that we have done earlier is for finding coefficient of variation. And why do we find out the coefficient of variation? Say you have a data, say for an example, you have the data for the goals scored by Messi, and you have the data for the goals scored by Ronaldo. Okay, so you will have certain number of matches, say in 2011, 2013. So out of 20 matches, yeah, this goals and this kind of data for both of them you have. Okay, and now the question is, say first 5 matches he has 20, first 5 say tournaments is 20, 23, 16, 18, and the last one say 20. And for the past 5 tournaments, the goals scored by Ronaldo, say for an example, 5, 12, 26, 18, and 25. Who is better? Don't go according to your liking. Talk in terms of the data that you have. Yes? Who is better? Tell me, please. Ronaldo or Messi? Who is better? Who is better and why?
So according to me, it's Messi because the consistency of the goals scoring in each tournament is more than Ronaldo.
Yes, exactly. Whereas the Ronaldo in some matches may perform very well, and in some matches he may not perform very well. So
Yes.
depending on this data, the Messi is more promising because uh, the central tendency, all of the observations, if you see, are around the mean. Okay, and therefore the variation in the data for Messi is very less, whereas there is a lot of variation in Ronaldo's data. That's why we declare that the Messi is good whenever you are looking at this data. Okay, so coefficient of variation is going to give me the final value by which I can compare any of the datas, and we can declare which is showing more variability or which of the thing is more consistent. So Carl Pearson suggested relative measure of standard deviation. Relative measure of standard deviation. So it is called coefficient of variation. Coefficient of variation, abbreviated as C dot V, and it is equal to standard deviation upon arithmetic mean into 100. So by notation, this can be written as sigma upon x bar into 100. So in this case, we are actually looking at the percent. Okay, so more the percent will tell me more variation is there. Yes, less the percentage, it will tell me the variation is less. If the question is who is more consistent, which you will look at?
Less variance.
Messi.
Less variance. So less variance will tell me the certain data is more consistent. More variation will tell me the data is not so consistent. Okay, so quick remark over here. more, or we will write this down in this manner. This will be very much better to compare the data. Coefficient of variation for the group A is greater than coefficient of variation of group B. So from this we can conclude that A is less consistent. A is less consistent. A shows more variability. The first one. The second one, coefficient of variation of A is greater than coefficient of variation of B. So B is more consistent and B shows less variability. Clear? Clear up to this? Third one, what do you think the change of origin will make an effect? So properties of variance and standard deviation. So I hope you got my question. So you have the data xi is okay, xi fi. And in the other one, what I'm doing is I'm taking ui as xi minus a, comma fi. Okay. So this data is of the form ui comma fi. What is this? This is called change of scale, right? Is it change of scale? Harshit?
Yes, sir.
Yes, is it change of origin or it is change of scale?
It's a change of origin.
Change of origin. So do you think that the variance and the standard deviation will change if I change the origin?
Yes, sir.
Will change of origin affect standard deviation or the variance?
Yes. It will affect the variance.
Okay. Saurabh,
Yes, sir.
what do you think? Will the change of origin affect the standard deviation or variance?
I think so. Yes, it will affect.
Khushi,
Yes, sir.
and do you think it will affect?
Yes.
Yes. Why? Yes, Hasnan, what do you think?
Sir, it won't affect because it will just change the range out of it. It will just shift ahead.
Exactly. So what does the variance and standard deviation calculate? As we have seen till now is standard deviation and variance. Both of them just calculates the deviation of the data from its mean value. Okay. Say for an example, you have this data somewhere here like this, and in this you will have the mean somewhere here. So I'll call this x bar here, right? So if I'm calculating variance, what you're doing is you're calculating its deviation from all these values like this. Okay. And when I say xi minus a, what I'm doing is I'm just shifting this. Either it will shift on the right, so the same diagram will come here like this. Okay. I'm not doing the change of scale, but just the change of origin. So I've just shifted. So when I shift, the mean will come here, say x bar, and its deviation from all the points will be the same. I mean, all the points are being shifted. That's why. So the first and very important property, variance, which is variance of x and standard deviation, are independent of change of origin, right?
Sir, will they change if there is change of origin? Origin, yes.
And then, can you please repeat your question?
Sir, will the variance or standard deviation will change if there is change of scale?
Yes.
No. Yes, sir. Change of scale.
For change of origin, it won't be affected, but change of scale, of course, it will be affected. But as you can see, okay, if this data gets shrink down by little amount, or if it is expanded, then this distance are going to change, right?
Okay, sir.
That's why the change of scale will affect, but the change of origin won't affect. So we'll write this down. The first point, so it is the change of standard deviation of x and variance of x are independent of change of origin. And second one, standard deviation of x, comma, variance of x depends on depends upon change of scale. Okay, and how does it depend upon the change of scale? So I have initially xi, the original variable is x, so I'll take u is equal to xi minus a by h, then sigma x is equal to h into sigma of u. Can anyone elaborate what is sigma u? Sakshi, what is sigma u? Am I audible? Aaron, am I audible, Aaron?
Yes, sir, you are.
Yeah. So can you tell me what is sigma u? Ritisha, Mittal, Tatsat.
So this would be, I guess, a standard deviation with respect to change of scale.
No, you're partially right again. Aditya Patel.
So, sir, the new sigma like formed after the change of scale.
Yes. So what we have done is we have the original variable as x, and then I have changed that variable uh, by x minus a by h. So I have a new variable u now. So for this new variable u, I can find out the standard deviation, and I have denoted it by sigma u. There was the previous variable x. So with respect to this x, we will get standard deviation. With respect to this u, we will get the standard deviation, and that I'm denoting by sigma u. Means that standard deviation of the variable u, sigma x, I mean the standard deviation of variable x, how they are related. If there is a change of scale by of h units, then the previous standard deviation is going to be h into the new standard deviation. I hope it is clear. So if you can simply try to prove this. It is a good exercise and very easy. So you'll be able to do this. I'll just write down one last remark. Yes.
Sir, means did we have to prove that sigma x is equal to h into sigma u?
No, yes, that is a homework and a good exercise. Try to prove it.
This
I'll just write down
relation.
the yes.
Okay.
The last one will write down the combined variance and standard deviation. First group first group of size n1 of size n1 mean x1 bar and variance sigma 1 square. We have the second group, of size n2 of size n2 mean as x2 bar and sigma 2 square as the variance. Then the combined variance, and the combined variance, say I'll denote it by xc square. So we have xc, sorry, sigma c square. So sigma c, I mean the combined variance of the group 1 and group 2. So it is given by n1 sigma 1 square plus d1 square plus n2 sigma 2 square plus d2 square. upon n1 plus n. Where d1 is equal to x1 bar minus xc bar and d2 is equal to x2 bar minus xc bar, and xc is combined arithmetic mean. Okay. In the next lecture, we will solve the examples based on this. I've given the link. Please mark your attendance.
Sir,
Yes.
sir, is my voice audible?
Yes, you're audible.
Sir, can you tell once again how did that D1 and D2 came as x1 bar minus xc bar and x2 bar minus xc bar respectively?
We are not going into the proof of this formula. Just note this formula down. Whenever required to find out the mean combined variance for the two groups, we'll use this formula.
Sir,
Okay.
where is the link?
Yeah, sir, I didn't got it either.
Me too.
Sir, it is
Yeah.
given chat. Chat isn't available at this time.
Now,
Yes,
got it?
yes,
Yes,
sir.
sir.